events going here. It's really nice. And so yeah, where do I see the bispectrum? So I'm seeing the bispectrum in the largest scales of the universe. So I'm going to motivate to you why it's interesting to look at these larger scales. I also see the bispectrum in the moon. So most of the work that I will show you has not been published yet. It's ongoing work, except for this stuff with the lunar array that I'm going to mention. And also I see bispectrum in a very nice thing, the power spectrum. So you can take the bispectrum for the power spectrum. You don't have to look at the 3-point correlation function all the time. So yeah, so these are the main topics that I'm going to discuss with you today. Okay, so to start with, what is the bispectrum? So to start talking about what is the bispectrum, for those unfamiliar with the term, I'm going to start with the power spectrum. So the idea of the power spectrum, it's very simple once you've thought a lot about it. The first time that you actually enter into contact with the power spectrum is not very trivial, but then you start understanding what it is, what it's all about. So for example, you can take a perturbation. Okay, so this is the total perturbation that you have in a field. It could be anything. And temperature, it could be the density in the universe. So you're looking at the total perturbation as a function of position, for example. And you can decompose this total perturbation into the wavelengths that sum to this total perturbation. Forgot to include here, this is from Alan Goode's paper about, the book. It's a very nice book by Alan Goode that Howell borrowed me during my PhD. Sorry, yes, lended me my PhD. And this plot is from Alan Goode's book. So you can do like this decomposition. And the power spectrum is basically telling you what will be the amplitude, like the weights that you're going to give for each of these periodic functions that are summing to your overall contribution, okay? So for example, here you can look, okay, this is going to be the inverse of position. This is the wave number associated with a particular wavelength. So you can take this wavelength, you can compute what is the corresponding wave number. You can go here in your power spectrum and check that, for example, 10 to the minus 2, this wavelength is contributing most. So you know precisely what is this wavelength that gives you most of the contributions to your total perturbations. And the power spectrum, each point of the power spectrum is giving you the amplitude for the contributions of these wavelengths. For the case of the bispectrum, things are almost the same, but now we are looking into the correlations of different scales, okay? So for the power spectrum, you take 2 points, and you're looking at this particular scale here, corresponding to this distance, for example, and you're looking at the autocorrelation of that scale. And this is giving you that the amplitude for that particular, for the particular wavelength, for your total matter contribution, for your total perturbation. For the bispectrum, what you're doing is that you're looking into a triangle, okay? So now what's happening is that if I look into my total density perturbation, if I look at my large scale structure, for example, this plot here, I take this triangle, I will ask you what is, how much in this large scale structure is this amplitude contributing to my total fluctuations? And then you go and you assign a certain weight for that particular triangle. You can also look what will be the contributions from very squeezed triangles, okay? So the angle between these two, you fold, you squeeze this triangle. This angle here, for example, becomes 0. And then you look how much of this squeezed configuration is contributing to your total perturbation, and you give this triangle a certain amplitude. You can also do the opposite. You can fold, like you can open completely this triangle, and you have also contributions for that particular configuration. Why is this interesting? So if you look at the large scale structure, you see that this field is very different from a Gaussian distribution. Okay, so if you think about if gravity was a completely linear theory, if you started with a linear initial condition and you evolve this with linear equations of motion, your initial field wouldn't develop any of these nice structures. So if this was a Gaussian field, you would see a completely Gaussian field in the end. But because you have gravity acting on this field, the Einstein's equations, they are nonlinear. So you start forming structures in a completely nonlinear way, and this will start generating these structures that can be, we can study this nonlinear evolution with the bispectrum, for example. So just to explain what's happening here, this is the bispectrum induced by gravity, okay? So if you look at your large-scale structure of the universe and you ask yourself, how much are each of these triangles contributing to my bispectrum, you can see that the large-scale structures show a preference for squeezed and flattened configurations, which means that your large-scale structure has a lot of filaments. So this is one of the ways that you can actually interpret this kind of plots of the bispectrum. So if you know how your structures are collapsing from your general relativity, from your theory, you can compute what is the prediction for the bispectrum, and then you can compare with the theory and see if you're understanding things properly. Right, so this is the basic idea behind the bispectrum. So in the case of the power spectrum, we had like each of those wavelengths have a certain amplitude contributing to your power spectrum. Here, we are going to assign different amplitudes to these triangles. So for example, if we had an equilateral triangle, we could say that this will have a certain weight. So your total bispectrum has a certain contribution from these equilateral triangles. So apart from understanding like how structures are forming and how to describe the density field statistically with the bispectrum, the bispectrum is very interesting because we can actually learn the initial conditions of the universe from this 3-point correlation function from the bispectrum. So if you think about the standard cosmological model, the lambda CDM, you have a lot of assumptions entering in this model. One of them is that you have general relativity. It's giving like the Einstein's equations to tell you how the universe is expanding, how the structures are forming. You have the cosmological principle, which you have to assume to fix the metric and to solve Einstein's equations. You have the components of the universe, that the universe is dominated by cosmological constant, and that you have cold dark matter as well. But you also need to assume something that's very important, which is inflation, for example. So with your standard picture, it's not complete in the sense that a lot of problems will emerge. So people in the 80s came up with this inflationary theory to describe the initial conditions of the universe. And basically, the idea is that you have this period of accelerated expansion, and the easiest, the simplest way to do this in the inflationary period is by considering a scalar field as low rolling and potential. And this will lead you to an accelerated expansion that you need to solve many of the problems that you have with the cosmological model that doesn't assume inflation. I'm not going to go into the details here, but basically you have a way to tell how this scalar field is behaving. So you have an action for your scalar field that's coupled, for example, can be coupled or not to the metric. So in the simplest inflationary scenario, you have just the standard self-gravitation of your scalar field. So that's the only gravitational contribution that you will have. And from this scalar field, if you perturb the metric, because this is a quantum field, you will have quantum fluctuations in this field, which will source fluctuations in the metric as well. These quantum fluctuations in your field will be responsible for the fluctuations you see in the temperature maps of the CMB, which will eventually evolve from this nonlinear collapse of general relativity into the structures that we observe. So perturbations in your scalar field from inflation will lead to perturbations in your temperature field and also in your final density galaxy that you're observing, the galaxy field. And you also need to do a quantization of the scalar of this quantum field, and you assume a certain initial conditions, like so you assume that this field starts from the vacuum. And what the bispectrum has to do with it. So if you take the simplest scenario, you will have a non-vanishing bispectrum because you have these gravitational interactions of the scalar field. So you will have what is called the gravitational floor. That tells you that the bispectrum for this standard scenario is very, very small. So pretty much like 0, okay? So the initial conditions are very, very close to a Gaussian field. So you don't have any of those structures. But as soon as you start breaking with the assumptions of your simplest model, so for example, if you start if you start quantizing your field from an excited state, not from the vacuum, then you start to see that these models will have this a certain peak, certain preference for these kind of configurations here. So this is like a flattened triangle, for example, okay? So you will have, in your initial conditions, this will not be close to the spectrum of an harmonic oscillator, but it starts to develop these non-Gaussianities, which we call primordial non-Gaussianities, because it's coming from these primordial physics. So you will have preferences for this kind of shapes of triangles when you look at your initial density field. You can also say, okay, I'm gonna add several fields to my inflationary period. So it's not just one single scalar field. I'm going to add multiple fields during this inflationary period. And by adding multiple fields, you have a peak, you have a preference in your initial conditions for triangles in the so-called squeezed configurations. So if you go, for example, in your CMB, in the temperature fluctuations, and you see that there is a non-vanishing 3-point function, a non-vanishing bispectrum peaking at this configuration, this will tell you that your inflation most likely had multiple fields, not just a single field. If you don't measure anything, then you can say that you had just one scalar field behaving like the standard, the simplest inflationary model. Another interesting thing about this configuration is that it tells you not only about that you have like multiple fields sourcing your accelerated expansion in the early universe, but also these kind of configurations have a very large contribution from bouncing cosmologies, for example. So if you don't like inflation, you like different cosmological initial conditions, such as equiperosis, which is this bouncing theory for your initial conditions for your primordial universe. This will give you a large contribution to these shapes in your primordial bispectrum. So it tells you not only about inflation, but tells you about more exotic models for your initial conditions. And you can also say that the action is going to have non-standard kinetic terms and can capture different interactions, different modifications from your standard simplest action. And if you break, for example, that your scalar field has a standard canonical term, then you start to see that you will have a lot of contributions to the equilateral shape. Okay, so if you have if you break all of these assumptions, so you don't have, if you're starting in your inflation theory from excited states, you have multiple fields and you have non-standard action, then you're going to have a combination of all these three shapes. And then your bispectrum is more complex, but each of these will tell you what are these assumptions that you're breaking. Okay, so this is why I think that the bispectrum is nice, and this is one of the reasons why I got into looking into seeing bispectrum everywhere, basically. The problem is that the bispectrum is very difficult to measure because you need to measure a lot of those triangles. So if you measure only few triangles in your survey, you have a lot of uncertainties on those measurements. So if you have more volumes, you can map more modes. And if you can map more modes, then you can look at more triangles for those different configurations, and then you can put tighter constraints on the bispectrum. Okay, so it's a difficult quantity to measure. You need to have a large volume to sample a lot of modes and to map a lot of these triangles. So just sorry to come back here, just to make this a bit more clear. So if you consider, for example, if you're interested in constraining primordial Gaussianities that peak in this squeezed configuration, you would like to measure a lot of these triangles in your survey. So you need to measure a very tiny K3, which means that you have two small scales correlated with this long wavelength perturbation, okay, because this is the inverse of the distance. So this corresponds to very large scales. So if you look here in this box, this would correspond to this blue curve. And if you have a very small volume that you're looking, you cannot sample the entire frequency of this curve. So you cannot get the period of this curve. It's very poorly sampled, so you need to increase the volume to start mapping the scales of interest for that particular shape, for example. And why am I telling you this? Because we are finally in the era of the cosmological surveys. So here is just a sketch of the development of cosmological surveys that we had. In particular, we are here. DASI is already operating. You can put, so in 2025, next year, Vera Rubin Observatory will start the legacy survey of space and time, LSST, and the expectation is of 10 to the 8 photometric redshift. So you can 10 to the 9, sorry, right? The 9. So you can put it like up here. But this is basically showing the spectroscopic surveys. So you have DASI here, mapping of the order of tens of millions of galaxies, and you have expectations to have a second phase of DASI, which is DASI 2, and this was about to start as soon as DASI finished the operation. So just around like 2030s, very, very early year. You expect to start this new survey, which is going to map a smaller region, but in more dense, with like mapping much more galaxies, many more galaxies. And you also have what is called this stage 5 surveys that they are under proposal. They haven't been approved yet, but the idea is that they are going to map hundreds of millions of galaxies in a very large range of redshifts. So you increase the volume a lot, and you increase the number density a lot. So it's not only interesting for the bispectrum, but it's also great for you to measure like the power spectrum. Okay.
Number of redshifts.
It's how so number of redshifts like the number of galaxies. Put it like this. So you're expecting like to measure 10 to the 8 galaxies, the redshift of 10 to the 8 galaxies. What?
How important is to have a spectrum?
So if you have the spectrum, then you have almost zero error in your spectrum, right? In your redshift, sorry. So you can map very precisely the 3 dimensions to the 3D. So like I figured like how the photometric errors could impact your bispectrum. Then so if you do with photometric surveys, if you have a non-vanishing error, if you have a non-negligible error for your redshift, then you have to do tomography. You can project your 3D structures in a 2D map, and then you don't work with the 3-dimensional bispectrum that I showed. You work with the tomographic bispectrum. I don't know how much that would impact the final measurements, but the problem is that then you are limiting to a 2D sphere, and the idea of doing these spectroscopic surveys is that it can actually do the 3D mapping, which will give you a lot of modes. It's very. Then you would be basically limited to I don't know. I cannot give you any for that. Sorry. If anyone knows like the impact of photosets for the bispectrum, like.
So there are projects in LSST to measure bispectrum. but I'm not aware of any forecast yet. No, sure. So there's a group from Mexico that is working by spectrum. That's the evidence.
And yeah, so the idea is to have huge volumes to sample a lot of modes, then you can actually constrain most of the configurations. So if you think about the squeezed configuration, how would that go for the bispectrum? If you have a, it's basically looking at the power spectrum. If you neglect one of the dimensions, right? So can the squeezed
still have triangles in two dimensions, right?
Yeah.
Plane, you can still
Yes. And so this is just a comparison from this paper. Leonardo Sanatori is one of the authors of the paper. And the idea here is to show, so these FNL, local, equilateral, and orthogonal, are pretty much like the weights that you give to each of those triangles that I mentioned in the beginning. So the FNL local is giving you how much those squeezed triangles are contributing to your total bispectrum. The equilateral is how much the equilateral triangles are contributing to your total bispectrum. The orthogonal is a combination. It's not any of these two shapes, but it's something a bit more different. The reason why we parameterize things in terms like that is because these inflationary models, you can actually, these inflationary models have predictions for those shapes. So this is a way to parameterize your inflationary theories. And here is just to show, if you forget about the constraints that you have on the cosmological parameters, the standard cosmological parameters, the thing is that the only constraints that you can have for FNL local, for example, which does not involve the bispectrum, is from the so-called scale-dependent bias. So they're not even showing it here. But the idea is that you cannot constrain these two shapes without the bispectrum. Okay, so you can see that those were the numbers that I got from this forecast from using BOSS galaxies. And then as soon as you move to DASI, that has more volumes, has a larger volume than BOSS, you can see that including the bispectrum reduces by a lot your uncertainties, almost it's more than a factor of 5 of reduction in these uncertainties that you get for these parameters. And one of the goals is to reach order 1 for each of these parameters, okay? Because basically how to distinguish inflationary models that have a very large amplitude for these and inflationary models that corresponds to the single field is lower on inflation. So if you get errors of the order 1 for each of these parameters, you can in principle discard all, if you don't measure like a large values for these parameters, you can discard all non-standard inflationary models. So this is one of the main goals of cosmological surveys. So you can see that adding the bispectrum is absolutely crucial. You cannot do it without the bispectrum for the equilateral orthogonal shapes. And for the local power, for the local shape, you can use the power spectrum, but adding the bispectrum gives you a bit more of information on this cosmological parameter. So this is just to motivate. We will be able to push some of the limits to these interesting numbers, which is not good enough. Okay, so 15 years ago, 10 years ago, I don't know, people were very optimistic saying that, yes, you can constrain FNL with order 1, with galaxy surveys. We're seeing that things are much more complicated than that. And actually, with all the predictions, all the forecasts in the literature, you cannot get constraints of FNL equilateral or orthogonal, not even like with stage 5 surveys. So it's a very tricky thing to do. But the FNL local, you can actually start playing around with it with the next surveys. So for the case of You mean why you can get the local but the other two not very well? Why do you want that? So I've been asking myself that question for a very long time, and the reason is that if all the models that, for example, are multi-field inflation, if you think of multi-field inflation, there are models that predict something which is of order 3 or 2. For equilateral and orthogonal shapes, also is like there are some ways that you can play around with your fields and with your inflationary theory, that you can tune these things to be a bit of order 1. It's not very, a very precise statement, but it's basically because if you have, so multi-field models, thinking about a final local, multi-field models will predict something which is larger than 1, but not that much, not like that larger. If you think about a single field lower inflation, that would be of order 10 to the minus 5, 10 to the minus 3. So it's just, this figure that they put for these parameters, but they can actually tell you something. So if you think about some models that are very like bouncing models, they predict something which was of order of 100, which has been discarded by Planck. So by measuring and this is also the power of the bispectrum for the case of DESI2. So this is not been published yet. This is a preliminary work by Sam Bridham. So I thank him for lending me this plot. But basically, this is showing how you improve, for example, if you compare. So these 5,000, 9,000 is the area of your survey. And so if you compare like for the 5,000 square degree survey, it's blue, if you compare with green, which is adding the bispectrum, you can reduce a lot the uncertainties that you have even on the standard cosmological parameters. So the bispectrum is a way to actually make cosmological surveys competitive with measurements from the CMB for the cosmological parameters. Okay, so from the largest scales, now that we're starting to measure the bispectrum in these very vast volumes, I prepared and not been great the way that I did this presentation, so I'm going to skip a lot of details here so I can show you more interesting stuff. I'm going to skip a lot of technicalities, but this is one of the ongoing works that I'm doing, and it's basically this: when you go to the very large scales, you have to account for the fact that the universe is not in a box. So you cannot say that the line of sight to each of these galaxies are the same. So each pair of galaxies, for example, if you're thinking about the power spectrum, these pair of galaxies have a particular line of sight. These other pairs have another line of sight. So you cannot assume what we do in standard like cosmology analysis, which is assuming that all the galaxies, all the pairs, and all the triplets, if you're thinking about the bispectrum, have all the same line of sight. So when you start looking at these vast volumes, these very large areas, then these kind of effects starts to appear. So this gives rise to this so-called wide angle effects. And the idea here is basically that this will impact how you project the galaxies in your survey. So when you do this cosmological analysis, when you do spectroscopic surveys, for example, you measure the redshift of these galaxies, but the redshift of these galaxies, they are impacted by, there is the redshift due to the expansion of the universe, but you will also have a lot of effects due to the peculiar velocities of the galaxies, for example, that will alter the redshift of your galaxies. So these will break the statistical homogeneous isotropy of your observations. And the way to quantify that is by looking into how your summary statistics, like the power spectrum or the bispectrum, decomposed according to your to some bases, which I'm choosing here to be the Legendre polynomials. So you can look at the dependence of these statistics with your line of sight.
So the wide angle effect is the same thing as the clear velocity effect, or it's different?
It's going to be, so when you do when you do this extension here of your three-dimensional power spectrum, you don't account for the fact that you have a dependence with the line of sight. Your power spectrum, your 3D power spectrum or bispectrum, depends only on the wave mode that you're looking and the angle that this wave mode is doing with your line of sight. But as soon as you have this wide angle contributions, this pair has a very different line of sight than this pair. So your power spectrum now depends not only on two variables, K and mu, but K, mu, and D. What is the line of sight to the observer?
So why this was, sorry, this was not taken into account before?
No, I mean, it was not relevant. So now we're starting to see if it is going to be really relevant for surveys like DASI and Euclid.
So why would it be irrelevant, or what sets the scale for being relevant or irrelevant?
The redshift that you're looking, so if you have a very local but a very wide area, then it's very relevant. Yes, but if you have a very pencil beam survey, a very small area, this is not very relevant. Also, if you have a larger area but very deep survey, like a redshift of 0.51, it's not very.
It's because of irregularities that you find in the line of sight. Is that because of fluctuations, large fluctuations in the line of sight? Is that the reason why this fact is important? I haven't seen this before, so.
Okay. So if you think, for example, forget about this 1/k, but think of this as distance. X and D is the distance from the pair to the observer. You can assume that if your galaxies are far enough, this D here is going to be large, such that this is very small. Okay, so the wide angle, you can do this wide angle expansion, which consists of taking your standard multiples and expanding these in terms of these powers of 1/d. Okay, this is the wide angle expansion. When the first term, the first order, is your standard plane parallel where none of this stuff matters. So if you assume that you have a very distant observer or very small, the galaxies are not very widely separated, but they're small. The separation is small, then this should recover your plane parallel limit. So it's very difficult to quantify how relevant this is, because that depends not only on the different lines of sight, the distance to the observer, but the size of the pairs of the scales that are involved. So it's a mix.
Yeah, I guess I have a question regarding the same thing. So I had the idea that, for example, the EGLEs and SDSS, they also try to push large scales. This implies that they didn't include this correction, if I remember right. So, but they still got like somewhat consistent source rates.
Yeah.
Does that imply that this effect is?
Must be very, it's small, yes. I'm gonna show you some plots for the bispectrum, not for the power spectrum. I didn't include that, I'm sorry, but yeah, they don't account, and apparently it's not that relevant. So this is under investigation.
So almost everybody uses the Yankees or Shimaro trick, which is not exactly what you've written there. So you transform basically one of the fields of the galaxy, and then you kind of get away with you get rid of some of the flat sky approximation and retrieve some of the larger scales. Now, in that assumption, you still have the n=0 term, that expression there that you have there. But in some sense, is this consistent with making that trick also, or you have to do how to actually compute the P of KD there? I mean, this is kind of
yeah, this is so I'm gonna.
This is how you do that, right?
I'm gonna show you. I'm gonna show you in a second, because that's not trivial. And there is this nice paper 2022 where it's Cosmo and another guy, Milad, I forgot his last name. They do perturbation theory expansion for that, and I'm going to go. Since you're asking, I can go very quickly through the details, but it's not very. It's a perturbation expansion in terms of the parameters S over T.
Okay,
Basically,
all right.
you can do that expansion.
So this is related to the flat sky approximation with rows. This is the
So this is a local plane parallel approximation, and it's already been used when you measure the power spectrum, for example, from BOS and EBOS. They use this local estimator, which is to each of these galaxy pairs, you assume that this is almost like in the plane parallel limit, but it's a local thing. It's not a global plane parallel where you fix all the lines of sight. So in the end, what you do is that you have here your standard power spectrum, which will depend for your lines of sight in each side of your survey. You have many lines of sight. You go in each of these local regions, you measure the power spectrum in that local region. This will give you these multiples of your K and D, PL of K and D. Then you do an average over the whole survey, over all the lines of sight that you have in your survey. So it's basically an average over the survey volume. So they do include these kind of effects when they measure stuff in the EBOS, because they consider this estimator, which is accounting for the different lines of sight that you have in your survey. The problem is that in the theory, they didn't need to model that, because on the scales that this should matter, the error bars are very large. You have the statistical precision to actually start seeing these effects for those measurements. So this is the paper that I mentioned. I'm just going to go very quickly through the idea. But what you want to do in the end is to calculate this local power spectrum. So you want to know how these statistics are depending for each of your lines of sight. So what you can do is that you know how to compute your 3D power spectrum, this P of K and D. What you do is that you go and you compute the density contrast of your galaxies, the full 3D in real space. You know how to do this. In this paper, they also include a lot of projection effects that have to do with gravitational redshift, effects of lensing. So they include all these information in this work. You know then how to compute these quantities in Fourier space, such that you know how to obtain your field in the configuration space from your theory in Fourier space. Okay, so this thing here with the kernels that you have computed, you can do this using, for example, your linear approximation. Then you can obtain your standard Kaiser term, for example. So here, the basic idea is that we want to compute this with the D dependence. And how the D dependence will appear, it will appear in this the exponential here. It is because you can assume that you have the flat sky, you can assume the plane parallel, and then this exponential simplifies, and then you recover your results. I'm not going to go through all the details because it's a very technical thing, but we can discuss this later. But the basic idea is that you want to break this assumption of plane parallel when you do this transformation from your Fourier quantities to your configuration space quantities. If you look here, then this is the kernel that you know how to compute for each of these local regions, right? So f of k dot x1 would correspond, for example, to the power spectrum, the anisotropic power spectrum in your plane parallel limit at this particular region here for this particular line of sight. But then when you do your when you compute to correlate with the second pair, you would have for a different line of sight x2, for example. So the plane parallel assumes that both x1 and x2 are the same. Okay. What we want to do here is not to go into this assumption, and we want to keep these as different positions really in the sky.
Because you're talking about, seems to me that you're comparing two pairs of points. So it's like a 4-point correlation function.
No, so what you're doing is that you want to compute your delta of x at a position x1. You want to compute your delta of x in position x2, and you want to do the correlation between x1 and x2 for those two different lines of sight, without assuming that x1 and x2 will correspond to a single, single line of sight. So you're breaking the isotropy there. So when you do the power spectrum, then you would get a delta function if x1 and x2 are the same, right? When you do the power spectrum. But then what you're doing here is that you're not supposing that. You are keeping both of them as different pairs in the sky. So it's a two-point function here. So this is one of the examples. And then if you assume that you have the plane parallel limit, then this exponential simplifies. You can integrate these things, and then you recover the standard plane parallel.
So x1 is the distance to one galaxy or to the average?
Is the distance to so you can parameterize the this pair here as the separation and the local line of sight.
So it's x1 and x2 in this picture.
X1 would be the position of this, x2 would be the position of that. Right, so yes, I'm sorry, I see what the question is. So you can do this calculation here, and then you assume that you have a single line of sight. What we're doing here is that we are computing these, assuming that they are almost close to a local to the plane parallel in that particular region. But then what you're going to do is that we integrate over all the lines of sight. So what they did in this paper is that they take the distance, x1 and x2 is the separation between the galaxies. And then in that expansion, you can use the separation over d as your perturbative parameter, and you do the expansion for the separation x over d. Then you can do this parameterization. I'm not going to go into the details because we'll run out of time, and I'm going to bore everyone, and I want to jump to other stuff, but we can discuss this. But the idea is that then you do the expansion for your S over D, and then you can compute the power spectrum for K. Here, eta is new, and XC will be a particular line of sight that you choose. So you show that these are all the corrections entering that sum that I showed. Yeah.
So you know that in the Kaiser effect, we could keep one term, which is, R, TTR of whatever delta you have, but there is another term, which is sometimes neglected, but I think you included there, which is the one, which is usually called the dipole term, right? Which is
depends on the selection function. Yes.
So I think you included in.
Yes,
in the rest of the spectrum.
Yeah.
Right? So
You include. So
it looks just like that. The 1 over X term is just like that term.
yes. But then, so just to summarize, is that they, in terms of that epsilon parameter, which is the separation of your pad over D, you can do this wide angle expansion. And what they did in this paper was to compute each of these contributions. I'm not going to go into the details of what these terms here mean. It's related to the kind of, projection effect, the pure wide angle contributions. So they do this full expansion in terms of for your power spectrum. And they show that if you include all these contributions, all these corrections that you're going to have, because you simply, in this theory, you're not assuming the plane parallel approximation anymore, but you're breaking the plane parallel. When you look at your power spectrum, you can have an apparent FNL in your power spectrum. So just once more, if you do so, when they make the measurements in EBOS and they try to constrain the FNL from your EBOS measurements, they are including these corrections in the estimator because the estimator doesn't assume a single line of sight. They use this Yamamoto, Bianchi, Scott-Maho estimator. But the point is that in the theory, they don't need to account for that yet, because they don't have enough precision. The error bars are very large at the scales where you would need to go to constrain FNL. S is the magnification bias. So this is a function of how your galaxies get magnified because you have a flux limited survey. So, but the main message here is that if you compute a power spectrum, no plane parallel assumption, no plane parallel assumption, but you include these effects, these wide angle effects, you will start to get an effect of FNL from this, which mimics your primordial signal.
So this effect on FNL in the power spectrum is encoded in what? In the skeleton bias power spectrum, or because in general you don't have FNL directly in the matter power spectrum, right?
Yes. So if you compare with the scale dependent bias of the 1/k².
Right. So the other plot then is like the value that they will estimate using the skeleton bias against the.
If you try to fit your scale dependent bias with the something that has no primordial Gaussianity but have this wide angle
Right.
contributions.
So can you back up a little bit?
Yes.
So then I think it's because of the scale dependence in here, right?
Yes.
So
Mhm. Exactly. So you have here, for example, this is a standard relativistic contribution, which has a 1/k² dependence. You also have here, for example, a case.
one of them, I think.
There are two terms, but you have a lot of k² scaling, which will appear. So here they're showing precisely these corrections for this k² scaling. So you have all these contributions that give you roughly the same kind of scale dependence on your power spectrum.
And this is still linear theory within the system, or?
For this, yes.
Okay.
So this is all been computed using, this is linear, this is your overdensity of galaxies in a linear theory, yeah. And they also then so you have these apparent FNL from your power spectrum. Problem is that you have the same expansion that you have to do for your bispectrum. So now when you look at your triangles, these triangles, you will have one line of sight to each of the galaxies that you have in your triangle. So you have three lines of sight. So then you can simplify that in terms of, this, there will be two expansions that you need to do for the bispectrum. So instead of 1/kd, you have these two contributions. And they did the same, but for the bispectrum. So they, you have to go now to second order. And then if you redo exactly the same steps, you go to second order, you look at your overdensity of galaxies, and you want to calculate what is delta of K1, delta of K2, and delta of K3 without assuming the plane parallel. You go and you do that expansion, and you will end up with your three-dimensional local bispectrum, which in the end you want to integrate over all the lines of sight in your survey. And it's a very massive thing to do, but you can actually then go and calculate what will be the total multiple that you're observing for the bispectrum. And this is something that Chris Addis, which is this PhD student in Queen Mary, University of London, is leading. And he took this work by Milad and not Milad, sorry, Nericolani and Scotimaho, and he went through all the derivations. He did this very nice code where we can actually then go and compute what will be these corrections. So here I'm just showing this is how the percentage difference, the relative difference from assuming your bispectrum and accounting including this correction. So I'm comparing these here in the y-axis is how much these corrections will contribute to your bispectrum. So you can see that, for example, for this particular configuration, where you have two sides of the triangles, they are the same, the corrections can be up to 5% for this particular configuration. He's using the other theta here means something else. So this is the completely flattened triangles. So the main message here is that, so this is the monopole and the quadrupole of the bispectrum. And it's not, that relevant. For some cases, you have like some percent corrections from your wide angle expansion. So unless you can measure the bispectrum with sub% accuracy for these configurations, this shouldn't matter. So I'm not I don't think that people in the DASI will actually include wide angle contributions for the bispectrum because they don't matter that much unless you have a very good precision for your measurements. And yeah, so this is just to, I'm running out of time. So here is a redshift of 0.2. For redshift of 0.2, it's where the contributions are larger because you have the triangles closer to you. So if you're looking here, it has a very different line of sight than over there. So if you increase the redshift, if you go to larger redshifts, then the corrections get smaller. So this is the overall impact.
In the power spectrum.
And the power spectrum, I didn't include the plots here because we are not looking specifically, but there's everything is done in this paper by Cosmo. Yeah. So the difference here is that, okay, we needed to implement this if we want to analyze some of these projection effects that comes from general relativity. I didn't tell you what this is, but it's basically that the main thing just to show is that you have contributions from general relativity when you look in your light cone. And if you want to, these general relativity corrections will give you a dipole for your bispectrum, which in the beginning people were like, okay, if we measure the dipole of the bispectrum, this will be a clear signal of general relativity predictions. But the thing is that wide angle effects alone, they generate a dipole signal, which is of almost the same order as your GR contributions. So it was a clear signal, it's not anymore because you have these corrections that you need to account for. So you need to do a proper modeling if your aim is to actually constrain GR effects with the spectrum.
Maybe I'm joking ahead a little bit, but I mean, let's say you do angular power spectrum, then none of this matters
No.
because there are no corrections.
Yep. So going to the angular basis, I think is the.
Why is that? Why there is no correct?
Because there's no approximation of that sky ever for anything. You're doing z, theta, and phi instead of x, y, z. There's no x, y, z.
Yes. Because that's what we do in photometric surveys. We do angular.
No. But you have to do it in a tomographic
Yes.
plane, so you have to do a full tomographic. Otherwise it lose all the line of sight information that you need. So it's not the same. I mean, it's the same in the sense that you are not using Cartesian coordinates.
Yep. So it's I think if you want to actually overcome this mess, if you have the precision to go to this scale, then why not go angular?
Well, this shows that you can also say, okay,
Yeah.
I like so much Fourier space and Cartesian coordinates that I'm willing to pay.
Yes, yeah.
That's what you have to pay.
I don't think people are very into paying the price for that, to be honest. So.
Well, we're discussing a situation where we don't have good enough data yet.
Yeah.
And we can see with the accuracy that we need to see to test the fundamental models anyway. So, for now, it's not relevant, but in the future, you have to, otherwise.
No, if you go to redshift
Never
of 3,
anything there,
yeah.
right?
Yeah. So this is just an advertisement to the Chris. He's running forecasts for this, I think for DASI and Euclid, to see if you can actually get the amplitudes of these wide angle effects for these measurements. So he's doing some forecasts. But here he also extended the fact that when you do these things in 3 dimensions and you measure this pair, so I'm sorry, let me go back just to show you very quickly. These 2 galaxies here, if you think of these as a light cone, so these different steps here correspond to different redshifts, different cosmic times. What they did in this paper by Cosmo is that they assumed that these are all at the same effective redshift. But as soon as you start to increase the redshift beam that you have in your survey, these will also have an impact. So it's what he's calling in the paper these radial corrections. Redshift, I don't remember what R is. This radial separation that you're going to have in your It's for redshifts of 0.4, for example, is where it's speaking the most. In this case, you will have some terms that will depend on derivatives, which they neglect, but basically it's not very relevant. So I think that sticking to an effective redshift, it's okay. You wouldn't have much of an impact. So that shouldn't be that much of a worry.
So can you maybe expand a little bit what they mean by GR effects in here?
So
Is
the GR effects is everything that goes beyond your standard Kaiser. So let me go to the power spectrum, which is easier to see. So when you do your 3D, when you compute your overdensities,
Yes.
this is the standard Kaiser. Everything,
So
you know
all
that.
that information is GR?
Yeah,
And what is the information? So then I'm confused because I didn't see the question well, but I thought that was wide angle thing.
yes, but so you have wide angle contributions
Right?
and you have GR contributions.
So all of them are there then. So when you mean the wide angle contributions,
You can extend wide angle on top of your GR corrections. So when I do these,
so when you mean the plot of GR only, it doesn't have, for example, which bar?
so you can take, for example, so GR only would be if you compute this in the plane parallel. So you assume a single line of sight for everything. Okay, so you go and you measure your bispectrum, your standard bispectrum, assuming a fixed line of sight for all the pairs.
Okay.
And then you will have to, if you go, then you do your GR corrections, there will be coupling with the geometry by doing this extension with some of these terms that appear here as well.
So the thing is that I think I'm still a bit confused, but can you have then wide angle effects without going to GI?
Yes.
Okay.
So for example, this is when you take your Kaiser term
Right.
and you do that expansion. So you take your bispectrum, you take
So
this
different effects.
regular Kaiser, exactly, yes. So GR here means, assuming plane parallel, you have your bispectrum that you expect. This is in the case here I'm showing is the dipole. But you can, so for the monopole, you can compute this and would be your standard gravitational.
So when you put GR, there is GR with wide effects.
Without the wide angles. When I put just without the wide angle effects, just
Wide
plain
angle effects is wide angle effects with GR.
without GR, with just Kaiser.
Okay.
And then total is accounting for all, is when you take all this maths and you do break plane parallel and you include all of your relativistic contributions. Yes, sorry, it's so just I'm going to skip all of the other places, but I see the bispectrum. I'm going to finish with this this plot here, which is basically telling me that if you try to constrain the exquisite configuration that you had from inflation, for example. So if you try to constrain the FNL local with the bispectrum, the presence of wide angle effects will generate some effective FNL. But in the end, you have like the, for just GR, if you assume that you have plane parallel, GR has a certain effective FNL, which is very big for the bispectrum for the specific configuration. And if you sum all the contributions, you sum everything, then you can see that you have a FNL, you would indicate an FNL of order -5 if you just go there and measure your bispectrum and you don't do the proper separation of, you know, I'm including wide angle, I'm including GR effects. Then you will also see an effective FNL from the bispectrum.
So this forecast again is for galaxies or for matter.
This is for galaxies. So you assume
Including skeleton and bias effects. So
Yeah.
you're including FNL.
No, so here is just comparing the scaling that you would have in the bispectrum with FNL. And you compare the scaling that you have in your bispectrum.
But only by spectrum then by FNL.
Yes. Take your bispectrum with FNL, you have p squared, for example.
Right.
Then that's what is mimicking. Yeah, so I was going to tell about the stuff that I did with Dark Ages, but I'm going to skip. But basically, just to close, is that I told you that it's very difficult to constrain the stuff with galaxies, with galaxy surveys. And if you think about the equilateral and the orthogonal shape, this is going to be not constrained, even like with the best surveys. So there is this very interesting work that people are doing by looking at the cosmic dark ages. And if you go to the dark ages, you go to redshifts of order 100, and then you have huge volumes. You can sample a incredible amount of modes. And then in this case here, for example, you can start seeing some very interesting constraints of order 10 to the -2 for these parameters.
Surprised actually that it gets so good because, you know, if you look at actual distance, it's not that huge of a difference. Because, you know, as you go from redshift 10 to 100, it's not like double or triple distance anyway, right?
It's not, but
So, you know, the number of modes in terms of Fourier modes,
it's
doesn't increase that much.
an order of 10, I think.
No, it's not. It's, you are decreasing, I mean, have already reached more than halfway across the surface of last scattering in terms of difference. Anyway, that's just
But you also,
I'm not saying that you've done the wrong thing there, but you know, it's surprising that you get such good results.
Yeah.
Just speak from
so there is some details here, which is if you go to this redshifts, you don't have galaxies, you don't have anything like that. So this is mapping the 21 centimeter fluctuations. So you're not limited by shot noise as well. You don't have the problems with your B, phi, FNL degeneracy because there is no halos, there are no galaxies there. So your prediction is very clear. And your nonlinearities, your gravitational structures is much smaller. So you are in the perfect regime to actually measure this stuff. So it's and this is something that I did with Phil Bull. We were looking into this because there's like the Joseph Silk, he wants to put the lunar interferometer. So we did this very quick forecast. It went wrong in many different ways. If anyone is interested in working with this, be happy to go into my code and see where the bug was, because this was for the proceedings paper that we published it last year. It just got published like in the early this year. So it was in a rush. So we just did a cosmic variance limited kind of analysis. So there's like plenty of stuff to do. Phil has some models for the interferometer in the moon, what the noise would be, how would that mess up with your constraints. But basically the idea is that it's nice if we can use the dark side of the moon to do cosmology with. And I'm gonna stop completely. I'm not going to mention the squeezed bispectrum. Just going to show here that we are doing some work. And this is Isabella, and she's the one that suggested the name of my talk. So I had something to say about it, but I'm not going to because it's been an hour already. So this is the summary, and thank you for your attention.
More questions. I'm chair.
So I agree. So, but is there any plan to because there are plans for going to the moon for gravitational waves. So once you are there, why not having an observatory? Are there reasonable plans?
So there is one which is going, I think, the end of this year, but it's a prototype. Andrzej Losey is leading it's called Lucy Night.
Google is working.
Google is working with Angie as well. It's the end of this year, I think, right? Or next year. It's like it's really soon. Like December this year, they will send a prototype to the moon. It's not going to be a real 21 centimeter experiment in the sense of, being able to do cosmology, but it will be mostly to actually start to characterize the signal, the foregrounds, the stuff that you have there. So it's just going to be a very small antenna that they will put in the moon.
Okay, for radio.
Yeah. Joseph Silk, he's really pushing this thing. And I think that the scales are like 2050 or something to start building large 21 centimeter experiments in the moon. But then to do like interferometer is going to be people planning like these inflatable antennas that you just put it there and it inflates and
Or even using a crater of the moon.
yes, there's a political fight for that. I'll
Yes.
discuss it later.
Is the moon specifically suited for radio or?
Yes.
Radio quiet.
So not only that, so these redshifts larger than 30 gets completely shielded by the atmosphere. There is a particular layer here that I forgot now which one it was. Ionosphere. Yes, the ionosphere. It shields all the signal that is for frequencies corresponding to redshifts larger than 30. So you cannot really observe from the Earth. So you should do like this in space with satellites, and then you have the problems with foregrounds because you have the sun, which emits a lot of foregrounds, radio waves. But you can also, if you put it on the far side of the moon, then you're shielded from the emissions of the Earth.
No, but there is even a crater in the moon
Yes.
that never get the sun. Because
Yes.
it's a crater.
Yeah, exactly. That's one of the reasons. So limits you cannot really cannot see from the Earth, and the other side is a perfect place to get shielded by these kind of foreground contaminations. But then you have all the technical issues of bringing the thing to the moon.
Send a couple of PhDs.
Well, then, thanks, everybody.
Before we split, we should come up with a proposal for next meeting. So the 10th of June. So I think